I need to start going to bed at like 8 o'clock. I was like, oh, I got advanced ed. Like 12 hours of sleep.
I had psychology.
Come on.
We got us submitted at 9:30. We were on time this week.
I asked you know this is advanced ed. So we're doing this a little differently. Normally I do the lab first and then I do the lesson, but we're going to do the lesson and then the lab just due to the fact that I was gone all weekend and it is not perfect. So, up to this point I've been doing stoichiometry, which really was taking some known quantity of reactant or product and trying to figure out the perfect relationships of all the other things that go with it. So if I'm doing if I have 11 grams of aluminum and I've got a certain chemical equation, how much grams of my other reactant will I need for it to perfectly react? Now, there is a set number that is the perfect amount that it would react with, correct?
Correct.
Okay, due to law of definite proportions, the fact that these ratios are constant, you cannot create or destroy matter, atoms, any of that stuff. Okay? Now, do you guys know the whole idea? Can someone tell me what the whole purpose of limiting reactant is really dealing with? Okay, so you're saying we may not have the perfect amount of both of my reactants that are the perfect relationship so that they both run out at the exact same time. Now, ideally, that would be awesome, right?
Yeah.
But in reality, not so much. Is that going to happen every single time? I mean, if it went perfect, yes, but very rarely will that happen. And I think last year you may have recalled my dumb example of the Rice Krispie treats and going in and realizing, oh, I don't have enough Rice Krispie treats to do my Rice Krispie cereal or make my Rice Krispie treats because I don't have enough of the ingredients to do it. And I was like, all right, we have to give up. We can't do it, right? No, we just had to what?
Make a smaller batch.
Scale it down so that the ratios worked. Okay, so that's kind of the whole idea here. Is in an ideal world, we would have the perfect amounts of all of my reactants and we'd be good, but not always does that happen. So, if I do not have the perfect amounts, one of them will run out first. And if it runs out, even if you have excess of the other, what's going to happen?
It'll stop reacting.
Because you need both for a reaction to happen,
It never
right?
stops reacting. It just equalizes.
Stop. Reaches equilibrium. Okay,
Yeah.
we'll get more into that later.
It unbonds and rebonds all at the same time.
Okay, so let's just start here. The one that runs out and thus limits. I mean, it kind of makes sense. A reactant that runs out and limits how much product can be produced. That's why we call that reactant the limiting reactant. I don't think I need to go too crazy more into that. I'm going to make this smaller because I'm going to probably use quite a bit of this screen. Like that. Is that too small? Can you see it?
Yeah, it's not good.
All right. Now, I don't remember what I did with you guys in regular chemistry. There's really two ways to do these problems. There's an easier way, but takes a little longer, 50% of the time. And then there's a faster way, which is only faster 50% of the time, but it's a little bit more difficult. What do you want to do?
The easier way.
That takes more time?
Yeah.
Yeah, it's easier, so.
And you said the other one only works 50%.
Well, it works 100% of the time if you're just solving for what's the limiting reactant, how much product is produced, but it doesn't work every time when you're trying to figure out how much excess is left over.
Can you just subtract them?
If you have it set up correctly, yes.
Oh.
Do the long way. Okay. All right, so it appears that we do not have what up here? Equation, okay, great. Good little review here. Nitrogen gas can be prepared by passing gaseous ammonia. Who can tell me what that is? What was that?
NH3.
NH4
Plus NH4 is
It's
the
NH3.
Oh, you're right.
Sorry.
It's in the problem.
It is, though.
Does it show it? Yeah, it does, doesn't it? Okay. over solid copper oxide. Who wants to take a tackle of that? Writing that formula.
CuO, also in the problem.
S, it's salt.
I got it.
Now you guys would have been able to figure that out. 2 minus, 2 plus, crisscross down, reduce.
Yeah.
Yes?
Yeah, but they don't have to.
Okay. Goes to produce. What does it produce?
N2.
Why not just
No,
N?
not, wait, not. Wait.
Okay.
Plus.
Oh, yeah, okay, yeah.
Plus what?
CU.
How many CUs? Like CU 2, 3, 1, 2. Just one. It's not diatomic. Just solid copper.
But is it stable by itself?
H2O.
It is, okay.
Enough. And then what? Okay, the question is this going to be, are we going to be able to eyeball this one? Should we try it?
Two
N2,
yeah, 2 NH3.
3 CU.
3 water.
3 CU.
That was quick. Is that right?
Yeah, 4.
That's right.
6.
You're right. You guys, wow, so good. Why are you struggling with that homework then? You guys got this stuff down.
That's not the
It's
hard
like
part.
100 times harder.
That's the easy one.
You're right. It was hard. I gave you 2 really hard over problems. I understand. Okay. So we've got the chemical equation, got it balanced correctly. Now we can start the problem. So how can you identify it's a limiting reactant problem without it saying what is a limiting reactant? Anybody know?
How much excess reactant left over? It's not.
What if it didn't give you anything about excess or leftover or limiting reactant? How would you know?
It has less of it.
Like based on the question, you mean?
Based on looking at the question, how would you know it's a limiting reactant problem?
There's a lot of it in the product, not a lot of it in the. Oh, just a smaller number.
2 numbers.
One.
Have you done any stoichiometry problem that's not a limiting reactant problem? Did they ever give you 2 numbers? They just give you 1 starting number and you can figure it all out. Because what they do is a lot of times in those problems where they give you 1 number, they subtly say this: reacts with excess, yada yada yada. So what essentially are they telling you?
That is a limiting reactant.
That the number they gave you is the limiting reactant.
Ah.
Does that make sense? Everybody, does that make sense? You realize when they just give you 1 number, you either have to assume they gave you the perfect amount of the other reactant, or they're saying we had plenty of the other reactant. Okay? So, we have to figure out which the limiting reactant, how much a product is formed, and that will come from what? Yeah, sorry. Maybe my question isn't clear enough. But we're not going to be able to figure out how much product is formed until we realize how much, or which is our limiting reactant. Why?
Otherwise,
Because we can do the stoichiometry for both, but not both answers are going to be right.
yeah.
Well, because you can only use the lower.
Yeah, you're going to only use the lower one because the one that's limiting is going to run out before you use the one that has excess completely. Okay, so that's what I was trying to ask. I'm just not I'm really bad at asking questions. How would you word that question? All right, so here's how I think is the longer way, but less thinking in the end. So you take both your reactants and solve them for the product.
Which product? The one that asked.
The one they asked for. Okay. How many grams of N2? So you would take a 3-step problem and you would do it for both.
But would the second reactant have any impact on N2? Would it have any nitrogen in it? Would the copper oxide have any impact?
These are both reactants. So they're both needed to produce N2.
Okay.
So what it's saying is, if I had this with excess of this, how much would it produce? If I had this with excess of this, how much would it produce? Well, we know they're both not in excess. One is going to be in excess and one is going to be living. We got to figure that out. So why don't you guys begin doing this, because this is just a review of what we did before I left on Friday. So you guys should be able to figure this out. Now, could I find a limiting reactant by taking these and solving for either of these two products? I could, but we're trying to kill two birds with one stone here. Does that make any sense? I can figure out which one's limiting by taking these numbers and solving for copper, or solving for H2O. But that would just tell me limiting reactant, wouldn't tell me how much of this got produced. So that's why I just kill two birds with one stone and for the winner's awful. And of course, I don't have the right. I have the other method on here. Right, but it might not be that close in some situations, so it's up to you whether you want to just eyeball it, because
Copper oxide divides by bigger molar mass and by a bigger number for coefficients. So
yeah, you're probably right then. But you also do start with more of it, so. But the difference between this and this and this and this, you're probably right. It's probably going to be CuO, but be careful with that. Are you guys done? Are you waiting on me? If you follow the unit train, you should be able to see how everything cancels out correctly. Now, I do not have the NH3 number because I didn't do it this method on mine. What was the NH? 14.9? Do I have a second on
I
that?
had 14.8.
It's really not off that much to really make a big deal.
14.80754.
It's only off.
That's true. You're right.
Okay? So, whether it's 14.9 or 14.8, does that affect identifying which one's a limiting reactant and which one isn't? First and foremost, who can articulate which one's a limiting reactant and why?
Copper oxide,
Why?
because it forms less than 2.
Okay? So, the most, if I react all of this, I can only produce 10.6 grams. And if I react all of this, I can only produce 14.9 grams. Well, looks like I can produce more N2 with the NH3 that I have, which means the CuO is going to run out first. Does that logic make sense?
Yes.
Okay? So we've identified that this is a limiting reactant, and we've also identified that this is the amount of product produced. Not the big number, the small number, because the one will run out. What else did they ask us? All right, how much excess is left over?
Is that what you do?
Just insert the bottom one to the top one and then subtract.
Yeah, so what you have to do with this is you have to start with your limiting reactant, which we said was what? So I'm going to start with 90.4 grams of CuO, and I'm going to convert that to what?
NH3.
Yep. And the reason why I'm going to take this and convert to this is because I know that this is going to run out. I want to know how much of the NH3 will react with it. Once we know how much, I guarantee you it'll be less than this number. It has to be. Okay? Once you do that, and a lot of these numbers you can just reuse, you just got to figure out where you got to put them. If that makes any sense. Like we've already figured out the molar mass of copper oxide. Okay, we already know that we have 3 moles of that. What do we got? NH3, so 2. And we already know the molar mass of my NH3. So you already have all the information, you just got to organize it in the correct way. And you should then figure out exactly how much NH3 you would need to completely react with CuO. What'd you guys get?
12.9.
Okay. Now, if you were to have gotten a bigger number than this, either you did it wrong, or you identified the wrong limiting reactant. Does that make sense? Okay? Because if this one's going to run out first, then I better have less of my other than what I have been given. So to finish, you do what?
18.1
Yep, 18.1 minus 12.9 should give you how much excess you have left over. 5.19 is what I have. That sound right? So I like this problem because it does encompass all the types of things you're going to see. The next one. Any questions on this before I erase? Good? Limiting reactants. Figure that out by taking your 2 reactant masses, convert to product. The smaller one is going to be the one you're going to go with because it came from the one that limited. Okay, then you take your limiting reactant, solve for your other reactant, and subtract. And it should be a lower number every single time. Okay. All right, theoretical and actual yields. Okay, this really isn't much more than what we've already been addressing and talking about. You should recognize these things from a year ago, or for some of you a couple years ago. Theoretical, this is going to be your math number. What do I mean by that? The number of what you get from your stoichiometry. Okay? It's what you theoretically should get. Actual would be what you get in the lab, or what you actually got. That make sense? Okay, and your percent mass should be your actual divided by your theoretical, I believe. I don't know how else I've done this. Yes. Okay? Do I have it in your note packet, or do you not have the equation in your note packet? Okay. So yeah, put actual divided by theoretical times 100, and you will have what you need. So this should just be, maybe this is a limiting reactant problem too. Let me see. Be careful because theoretical yield problems have to give you an actual, so be careful. You may or may not have to do limiting reactant with it. Depends. Okay, let me see. Suppose you got this, reacts with that. Calculate the theoretical yield. So it looks like it is a limiting reactant problem because I have 2 reactant masses. What's this? It's the actual, okay? So we need to take this, figure out the limiting reactant. Okay? Once you do that, the product that comes from the limiting reactant would be your what? Theoretical. Okay? Now for the sake of time, I'll just give you the equation. 2H2 plus CO goes to produce balanced. Let's just quickly take this and convert it to grams.
Holy buckets, that's a lot.
Then you do what? You would convert both to your desired product, which there's only one product, so that makes it kind of easy. So if you guys got any numbers, I did this the old way, so I only have one of the two numbers. 6.82 times 10 to the 4. Anybody get that one? Anybody? Or you guys just waiting for me?
Oh, what number?
They answered.
Oh, yeah.
What did you get? So this one's going to be bigger, this one's going to be smaller. So this would be the number we would use for our theoretical yield. Yes? Why? Because it's a smaller number and it comes, therefore it has to be the limiting reactant, has to be this.
Wait, what? I got one of the numbers. The bottom number is what I did not.
That's the right number, that's my number, but that's the right number.
Is it wrong?
What?
It does kind of divided by 2.02 divided by 2 times 32.05.
Do it again, I bet you'll get it. So you take the 6.82 times 10 to the 4, and your actual is what? 3.57 times 10 to the 4 times 100. You should get the correct answer, which is, that is not a very good theoretical yield, or a percent yield. Something like that. That is a bad percent yield, real bad.
Not even close to the range. If we did that on that test, I'd be like, oh, I did something wrong.
No, don't do that. Just double check and make sure, but it's very possible that it could be a bad theoretical yield. Did you get it the second time, Rylan?